weighing the continents with space gravity missions. This is work I've been doing for the past probably 7 to 10 years. And this stuff is really cool. It's amazing what can be done with satellites. So what I'm going to go through is some of the ways that these measurements are made and what they can tell us about what's happening on Earth. Let's just get this going. So before we get to that, I'd like to ask you a question, and I'd like to get you just to type your answer to this question into the chat. Who knows what the acceleration due to gravity is on Earth? If you know, just type down the number in meters per second squared. Do we have any answers yet?
We do. So we've got a lot saying 9.8, 9.81, 1G, which is also correct in a different unit system to the 9.81 is the same. Lots very close to 9.8.
Okay, 9.8, 9.81, that's what we get taught in school. The real answer to that question is, believe it or not, it depends. It depends upon where you are when you measure gravity, and it depends upon what day you measured gravity, because it's changing all the time. So if you measure gravity, if you're in a 5-story building and you measure gravity on the ground floor, and then you took your instrument up to the top floor and measured gravity again, it would actually be less on the top floor. So the strength of gravity depends upon the distance you are from the center of the Earth. And we have instruments that can measure those differences just from one floor to the next. So in fact, you weigh less on the top floor of a building than you weigh on the ground floor of the building. Now, it also depends upon when you measure it, because the strength of gravity on Earth changes with time. And this is a really strange concept, but gravity is dependent upon the mass. And so if you have more mass in a place, you will have stronger gravity. If you have less mass, you will have weaker gravity. Now you might think, okay, well, the mass of the Earth doesn't change, but actually it does, and it changes all the time. The shape of the Earth is changing all the time. And for those people in Canberra, it's just rained a lot. It was almost snowing at my place, actually. And because it rained, the ground is now wet. All of that water is sitting in the soil, and now the soil is heavier than before it rained. And we can measure the change in gravity caused by that water in the soil. And that's what these are space gravity missions are all about, measuring changes in mass on Earth, changes in the gravity field on Earth, which are caused by changes in mass. And so then we can quantify how the mass is changing across the Earth. So we can measure all sorts of different things. So here's an example of the changes in mass in September 2010 as measured by these space gravity missions. The red parts here are where there is less mass than normal, and the blue parts are where there is more mass than normal. So what this is actually showing you here is just the hydrology across the Earth. Across here in September, this is the wet season. So this part of Africa and this part of Northern South America is the wet season, as it is in India and Southeast Asia. And in the other hemisphere, the Southern Hemisphere, it's the dry season. So the whole of the Amazon basin is drier than usual, as is Northern Australia. Now, in addition to that, there are some bits like here in Western Antarctica, up here in Greenland, and over here in Alaska, where it's very red, almost white. So it's almost off the scale here. And this is because these are ice-covered regions, and these regions have lost mass. The ice has melted and the water has flown into the oceans, and now it weighs less than average. This is because of climate change. So these glaciers here in West Antarctica are losing mass at a very rapid rate, and that's causing sea level to increase. Now, an interesting story, before these space missions were put into orbit, built and put into orbit, there were two people who had a disagreement about whether this would even work. One of them said, when this is in orbit and we can do the calculations, we will come up with a map here which shows absolutely nothing. It'll just be a blank map. There'll be nothing to see. And the other guy said, it's my idea, this mission, and I'm sure it's going to work, and we're going to see all sorts of signals. And they had a bet, which was a bottle of wine, and they launched the mission, and it worked really, really well. And so one guy had to buy the other guy a bottle of wine. Okay, what can we see? The wet, dry seasons, the Alaskan glaciers losing mass, Antarctica and Greenland losing mass. We can also see changes in the crust of the Earth uplifting because of massive loss of massive ice sheets 20,000 years ago. Now, if you look closely here in the northern part of Canada, 20,000 years ago, there was an ice sheet sitting here, a bit like over Antarctica, and it was about 3.5 kilometers thick, and it has now all melted away. But because of that enormous mass of ice sitting on the continent, it pushed the Earth, the crust of the Earth, down into the mantle, which is kind of like the fluid part of the Earth. And then the ice melted, and the crust is still coming back up very slowly. And because of that, there's an increase in mass in that part. And so we can detect the change in mass. And this is because of what we call glacial isostatic adjustment. We can also measure ocean signals, but I won't go into that today. So what are these missions? The space gravity missions are known as GRACE, the Gravity, Recovery and Climate Experiment. There are 2 satellites. They're about 400 to 490 kilometers above the surface of the Earth. They follow each other around the Earth, about 200 kilometers apart. It takes them an hour and a half to travel all the way around the Earth. And we measure the change in distance between those 2 satellites. So they're 200 kilometers apart. We measure the change in distance with an accuracy of 1/10 of the thickness of a human hair. So you imagine if you can pull one hair out of your head and get 1/10 of that size, that's the accuracy with which the measurement is made between these 2 satellites. And they're 200 kilometers apart. So that's like one satellite is nearly at Goulburn and the other satellite is in Civic. It's absolutely amazing that this can be done, but it can be done. GRACE was launched in 2002. In 2017, it stopped working. And then GRACE Follow-On came along, which was a replacement mission that does a very similar thing. It was launched in 2018 and it's still operating today. Now, how does it work? What we're measuring is the distance between the satellites. So how does that tell us anything about gravity? It's a good question. Imagine you've got 2 runners that are running along a road and they're joined together by a rope. The first runner coming along comes to a hill and starts running up the hill and will slow down because it's harder to run up a hill. The other runner will catch up because the other one's still running along the flat, and so the rope between them would become a bit loose. Then the second runner starts running up the hill, and so they're both running up the hill. Then the first one goes over the top of the hill and starts coming down, and then the rope will increase or will become tighter because now the first runner is speeding up. Then the second one goes over the top, and so on. If we can measure the change in the rope, then we can know whether the runners are on hills going up or coming down. And so it is with the strength of the gravity field. If the gravity is stronger on Earth, then as the satellites come towards it, they are actually accelerated, they're pulled towards that stronger gravity. And so the distance between the satellites changes. And this is going on all the time as the satellites are orbiting around the Earth. And it's changing the distance between the 2 satellites. So that's what we can measure. And we can then use that measurement to tell us how strong the gravity field was on Earth. And from that, we can work out how much water there would have been, how much ice has been lost, how much the crust has uplifted. It's really, really cool science. It is rocket science. It's just great fun. This is a cartoon drawing of what's inside one of these satellites. So there are tanks of rocket fuel, which is used to burn thrusters to keep the satellites pointing to each other, because we have to measure between them. So they can't kind of look off in various directions. They have to be pointing to each other. Then we have various GPS satellite systems. There are things to measure the atmospheric drag and the solar radiation pressure, so the particles coming from the sun that are hitting the satellites. All of these things affect how the satellites orbit and fly around the Earth. So that's kind of what it looks like in concept. And then over the outside is a covering, which is essentially solar panels, because that's what recharges the batteries to keep the satellites working. These are the actual 2 satellites as they were being built. So here you can see the GPS antenna, and there are all sorts of other bits and pieces. And then these are the satellites with their solar panels on the outside. These things were about 4 or 6 meters long. They weighed about 600 kilograms and went up on a rocket, and then they get popped off the side, and then they just start orbiting around the Earth. The forces acting on the satellites. There's the gravity force of the Earth. So the Earth is pulling these satellites back to Earth. Any satellite that's going around in an orbit is effectively falling towards the Earth. And as it falls, it moves forward, and it just keeps falling. They're also affected by the pull of the gravity of the sun and the moon and all the other planets, Jupiter, Saturn, and so on. And we have to account for all of this when we're doing our calculations. Gravity changes because of atmospheric mass. So if we have a high pressure system, there's more mass in the atmosphere, and that will be attracting the satellites more. Ocean tides, when it's high tide, there's more water. When it's low tide, there's less water. The tides are between 0.5 meter and 6 meters across Earth. We have an accuracy of being able to measure about 2 centimeters of water thickness. So ocean tides are really important signals as well. All of these things affect the satellite and the way that the satellites orbit around the Earth. Then we also have these other forces, the solar radiation pressure, which is coming from the sun, the drag. So as you're riding your bike down a hill, you get a wind blowing in your face, and that will slow down how you go down the hill. Atmospheric drag exists for these satellites as well, because they're only 400 or so kilometers above the Earth. So they're in the Earth's atmosphere, and we have to account for that. And then all the thrusts of where they're keeping the satellites oriented to each other, they affect the way the satellites orbit as well. So what can we measure? We can measure soil moisture. It rained in Canberra. We could measure that gravity is now stronger in Canberra than it was before it rained. We can also measure groundwater. So if there's no change in rainfall, and if there's no change on the surface of the Earth, but people are pumping out the groundwater, they're taking water from under our feet, and that means there's less mass, and therefore there will be weaker gravity, and we can detect that. Now, as the ice sheets are melting in Antarctica and Greenland and Alaska, that water that melts runs off the continent and flows into the oceans. And that means there's now less mass on the continent and there's more mass in the ocean. So we can measure the increase in mass of the ocean, and you express that as a height of equivalent water. And since the start of this mission in 2002, the ocean has gone up by about 25 millimeters because of melting of Greenland and Antarctica. Now, I reckon if you went down to the beach, you wouldn't be able to see 25 millimeter increase in the ocean height, because there are waves, because the tide is high or the tide is low, and you just can't tell by eye, but you can tell by taking measurements using satellites. So if we look at Antarctica, this is the West Antarctic area. You may have heard of Pine Island Glacier, which is just in here, and Thwaites Glacier is here. These are the main 2 glaciers that are losing mass. And this is what we can detect with GRACE. So we're looking here at about 6 meters of mass loss since 2008. So you imagine a big ice sheet. We have carved off the top 6 meters of that and put it into the oceans. And this is why the oceans are increasing in height. In Greenland, you get a similar thing. It's all around the coast. It's all around the edge. In the center of Greenland here, there's actually a little bit more snowfall than there used to be. So it's gaining a bit of mass in the middle, but it's losing a lot of mass around the outside. There are a lot of glaciers here, and I'll be honest with you, I can't even pronounce their name. They're very complicated names. Okay, so here's what's happened in Antarctica. Relative to the beginning of the mission at 0, we're now down, and averaged over this whole area, it's lost about 2 meters of ice, but in particular locations, it's as much as 6 or more meters. There's also over here, it's called the Totten Glacier. This is just near Casey Station, which is one of Australia's Antarctic bases. This is really starting to lose mass in a serious way now. And if this gets going as well, we're in even more trouble than we're in right now. In Greenland as well, it's focused on particular glaciers. This one is called the Jakobshavn Glacier. I won't try the other names. Again, starting from 0, we're down at 3 to 4 meters. In particular places here, it's also up at around 6 or 7 meters of ice is what we have lost. And this is accelerating. If you look at this, if you were to put a straight line through this, it would be up here. So this is curved. And that means that as time goes on, the glacier is losing more and more mass, which means that sea level is rising faster and faster. Okay, so what can you do about this? We need you guys in 10 years' time. We need people who can do these sort of measurements, do these studies, design and build these satellites. So we need you guys to be doing maths and physics at school. We need you to learn how to use computers, not just to play computer games, but to program the computer, to make it calculate the orbit of a satellite. We need you to care about the climate. You can't vote yet, but in 10 years or so, 8 or 10 years, you can vote. And if you don't like what the government is doing or not doing, vote them out. Vote for someone who will do something. Go to university, learn how to do this, and become a part of Australia's space industry. You know, we have a space agency now. It's been around for a year or so. Get involved. We need people involved. So my team involved in doing all of this work with me. I have a few academics. I have a couple of young postdocs who are doing research, and I have a couple of PhD students also doing research using the GRACE and the GRACE follow-on satellites. Now, something interesting here. We academics, we're grey-haired old men, balding grey hair. My younger people in the team are women, and I think that's great. There's a future in science for all you girls out there who think you can do this stuff. You can do it, and we want you. So get to work, learn some maths, learn some physics, and come and have fun doing science. Thanks, guys. I'm happy to answer any questions.
Right. Thanks so much, Paul. That was really amazing to see how we can actually, it's just awe-inspiring to think we can make these measurements. It's incredible. So there have been a lot of questions, so we'll jump right in. And perhaps to start with, some people were wondering about the melting of the ice. Some people, Milta asked, what is causing the ice to melt? Elric asked, why do the ice sheets melt and fall away? Sort of how does that work? And Guinevere has asked, how much is a gigaton of ice? So how fast is the ice melting? So could you explain for the young stars, why is this happening? How fast? Perhaps what can we do about it?
So there are two main reasons why the ice sheets are melting. The first one is because the air temperature, the atmosphere is warming. So this is the greenhouse effect. When we have more carbon dioxide in the atmosphere, it traps the energy coming from the sun in our atmosphere, and therefore the planet is warming. So because the atmosphere is warmer, that heat in the atmosphere melts the surface of the ice sheet. And especially in Greenland, you get a lot of melt in summer, and that water then runs off into the ocean. To some extent, it comes back a little bit in winter as snowfall, but there's more melt than redepositing of snow. And so then the effect over time is that it's losing mass. Now that's happening to some extent in Antarctica, but also in Antarctica, the ice sheets are below sea level, and therefore the ocean actually comes up and hits against the wall of the ice sheet, and the oceans are warming. And because of that warm water that's coming on into contact with the ice sheets, it's melting away, it's eating away at the ice. So you imagine you have an ice cube and you put it into a glass of warm water. The water will attack the ice cube and it will melt and decrease in size. That's exactly what's happening down in Antarctica. So they're the two main mechanisms for how it works. How much is a gigaton? A gigaton is 1 billion tons, and a ton is 1,000 kilograms. So a gigaton is 1 trillion kilograms. It's a lot.
Right. Thanks, Paul. I've also got some questions for you about how these measurements actually work. So somebody has asked, what are the tanks that are on the diagram of the satellite? It has sort of these two large tanks. What do they do?
It's fuel. It's rocket fuel to power the thrusters on the satellites so that they can be continually pointing to each other, because they're 200 kilometers apart, but they have to be looking directly at each other. And so as they're flying around, about 800 times a day, the thrusters are fired in order to keep the satellites aligned to each other.
Wow, it's similar in the having these lasers working over a long distance to the gravitational wave measurements, but it certainly would be a lot more complicated putting that sort of thing in space, I imagine. So
yeah,
that sounds very important.
Yeah, well, the GRACE follow-on mission does have a laser as well. So a lot of that technology was developed at ANU in physics. They built some of the prototype equipment, which is flying on the GRACE follow-on missions. And actually, there's one guy at physics, Professor Kirk Mackenzie, who had his hands inside the GRACE follow-on satellite, bolting on some of the laser equipment. So we have someone in Canberra who literally has built a satellite and it's now orbiting the Earth. It's pretty cool.
Yeah, that's very cool. Sort of all of these skills that maybe the young stars will go on to develop and perhaps work on satellites themselves one day. And actually on that note, Ash has asked, as a kid, can I join the space agency?
The space agency is a government agency and they don't have a big budget. I'm not sure they're employing kids at the moment, but what you could do is keep in mind that Australia will have a space industry. And what we're trying to do at the moment is build up the businesses and build up the knowledge base of Australia so that we have the engineers and the scientists who can come up with really cool ideas like the GRACE mission and then build the instrumentation and launch things into space.
Yeah, it's a very exciting time. So another question about the satellites specifically. How are the measurements affected by the moon, the gravitational pull of the moon?
They're affected in a very substantial way, so that if we didn't calculate the gravity of the moon, we would not be able to calculate the orbits of the satellites properly. The reason we have tides on Earth in the ocean is because of the gravity field of the moon. So it's constantly pulling the water towards the moon, and that's what causes the slosh of tides across the Earth. So just as it will affect water on Earth, the moon's gravity field will affect a little satellite orbiting around Earth.
Right. Okay. So there's all of these different factors at play besides just this change in gravity at the Earth's surface. So Joachim has asked, how can you control for errors in the measurement caused by some of these disturbances that might be in the satellite or other factors in space?
Yeah, good question. We can't control the errors in those measurements. And that's where all the difficult work in the science of analysing the data, that's where it all sits. So we have to try to identify the errors compared to the signals. So when you get a measurement, it's a sum of both the signal that you want plus the error in making the measurement. And no one ever really knows the difference between those two, how much is signal and how much is error. That's where all the fun begins, in writing the software and trying to work out ways to separate signal from error. If you get it right, you end up with plots of the gravity field like I showed you. If you get it wrong, especially with the GRACE analysis, you just get north-south stripes. Really big positive signal, big negative, big positive, big negative, and it doesn't look anything like reality. And you can look at that and go, well, they got that wrong.
Right, okay. So some people have also asked about the launch of the GRACE satellites. How were they launched, on what kind of rocket? And Talia has asked, how do these satellites launch without a person in the rocket? How do we get these satellites into the correct orbit and make sure everything's correct and working properly?
Yeah, very good question. It's a little bit beyond my expertise, but I can have a guess. So it's done with very careful engineering, and I think the GRACE satellites were launched on a Falcon 9 rocket, and the GRACE follow-on satellites were, I can't remember, a SpaceX rocket, I think. Now, how do they push them off the rocket to put them into orbit? They have to know what altitude the rocket is, but that's known through measurements on the rocket. And at the appropriate time, there is some sort of clamp that is released, and then some trigger that would force the satellites to fly away from the rocket. So they essentially just break off and go out into space. And once they're flying like that, they then, I watched the launch of the GRACE follow-on mission, which was in May 2018. And they launched from Vandenberg Air Base in California and headed south down the Pacific Ocean. The first time that the mission control were able to communicate with the satellites was as they flew over McMurdo Base in Antarctica, and one satellite talked to them, but not two. And then they had to wait about 15 minutes for the satellites to fly under Antarctica and then back up into the Northern Hemisphere when they got their next chance to talk to them. And then the second one talked as well. So once they had communications with the satellites, they're then able to start giving commands to fire the thrusters so that they can start to orient them and put them into the correct orbit. It's all very carefully calculated. They only get one chance at this. And if something went wrong, then it would take probably 3 or 4 years to build a replacement mission, assuming there was money to do so. It just has to work first time. There's no second chance.
Yeah, it sounds like there'd be a lot of time getting all those calculations perfected. I have another question about the nature of the changes in the ice from Ilse and Felix, who have asked, are glaciers and ice sheets made of salt water or fresh water? And they're asking, is this important? So what might this mean for the consequences of the ice melting, perhaps?
They are fresh water. Any water that's sitting on continents is fresh water in ice. The sea ice that forms around Antarctica is frozen salt water, but for the sea ice, the salt actually leaches out of it, so it comes out through the bottom, and it ends up being mostly fresh. But it's a very good question about what happens if you melt a freshwater glacier or ice sheet. What does happen is that fresh water then flows into the ocean beside the continent, which then means that the ocean there is less salty because you've added fresh water to it. And therefore it's less dense, because if you add, salt water is more dense than fresh water. So if you add fresh water to the ocean, it becomes less dense, and the less dense the water, the more it expands. And so adding fresh water to the ocean actually causes sea level to rise, not just because you added more water to it, but because it becomes less dense and therefore it expands. Now, there is a risk that in the Northern Hemisphere, if Greenland continues to melt, it's adding substantial amounts of fresh water into the northern part of the Atlantic Ocean. And there is a risk that fresh water addition to the ocean could affect the ocean circulation and shut down the major currents in the North Atlantic Ocean. And that would have serious ramifications for the climate in Europe and in North America, because it's those currents that transport the heat up into that part of the area, If you stop that current, you stop the flow of heat, and then it will get much, much colder up there.
Great. Right. Thank you so much for answering all of these questions. This brings us to the end of our Q&A session, but I have one final question for you, Paul. What's your favorite part about being a geophysicist and a mission specialist?
Teaching people. I love teaching people. I love being able to open people's eyes to things that they never thought was possible, and seeing them learn stuff, and it's just great fun. I like talking to kids in primary school. I give talks in high schools. I teach undergraduate students, and I teach PhD students, and it's a lot of fun. I also like playing with satellite data. I think it's great. You get to take your head and imagine yourself up on the satellite looking back down at Earth, and it's really good.
Yeah, that sounds very exciting. So thank you so much for being here with us today and sharing your knowledge. I think this is the inspiration and motivation for the young stars to now go ahead and make their own measurement of gravity. So thank you so much for your time, Paul.
Thank you all. Enjoy your experiment. Oh, by the way, if you all get the same answer, exactly the same answer, you're all wrong, because gravity is not the same everywhere. So take the measurements and don't try to get the same answer as someone else. Just get the right answer for where you are.